Deep space is a collection of lethal threats. It presents cosmic radiation that fractures human DNA, a vacuum that forces air from the lungs, and Martian regolith saturated with toxic perchlorates. To navigate these conditions, a conceptual mission like the Carver-Lacks Horizon requires a closed-loop architecture of survival. Every component, from the oxygen recyclers to the hull plating, must perform perfectly to sustain life. Most of these systems aren't being invented from scratch today. The essential blueprints for off-world travel were actually drafted decades ago. To reach Mars, we are relying on a historical lineage of Black scientists and inventors who originally developed these methods of survival to solve problems on Earth. This mission begins at the microscopic level with Henrietta Lacks. In 1951, doctors took a sample of her tumor cells without her knowledge, cells that would eventually travel farther than she ever could. Henrietta's cells, known as HeLa, proved to be immortal. They divided indefinitely in labs, and during early Soviet space missions, researchers discovered they were actually thriving in microgravity, multiplying faster than they did on the ground. Most human cells follow the Hayflick limit, a biological clock that ticks down to zero after about 50 divisions. Henrietta's cells ignored the clock, doubling every 24 hours and refusing to die. Today, HeLa cells serve as biological sensors on spacecraft. Because they react to radiation more sensitively than mechanical gauges, they provide the crew with an early warning when solar activity reaches dangerous levels. Moving from the cell to the individual astronaut, we face the most immediate mechanical hurdle: breathing in a completely toxic, airless environment. In 1912, Garrett Morgan developed the safety hood. By using a long tube to draw cool air from the floor and a wet sponge to filter out fumes, his device allowed workers to breathe through the thick, toxic smoke of tunnel explosions. The filtration logic of Morgan's hood is still visible today. It shares the same basic oxygen loop and carbon dioxide scrubbing paths used in the portable life support system backpack that keeps an astronaut alive in the vacuum. Those backpacks feed into suits that must withstand absolute pressure differentials. The 21 layers of the Apollo spacesuits were hand-sewn by Black seamstresses. They brought extreme precision from the garment industry to ensure no air leaked through a single stitch. The same expertise that pulled breath from a burning tunnel and precision from a clothing factory now protects human lungs from the vacuum of space. Beyond the individual suit, we have to consider the ship's macro environment. A multi-module vessel needs to manage safety and communication without constant human intervention. In 1887, Alexander Miles patented automatic elevator doors to prevent passengers from falling into empty shafts. That design evolved into the fail-safe airlock hatches that automatically seal off a module the moment it loses pressure. To prevent the ship from colliding with other modules or landers, the navigation system relies on the logic of Granville T. Wood's induction telegraph, a 19th-century invention that allowed moving trains to communicate and avoid crashes. These machines only function because of the mathematical framework beneath them. Katherine Johnson calculated the precise trajectories and launch windows that made spaceflight a reality. Mary Jackson analyzed how air moves around high-speed objects. She provided the aerodynamic data needed to ensure a ship's heat shield survives planetary entry. But the final challenge isn't just arriving, it's surviving on the surface. Martian regolith is essentially crushed rock, baked by radiation and devoid of life. To turn that dust into soil, we look to George Washington Carver. He spent his career restoring the exhausted, nitrogen-depleted soil of the American South. Carver pioneered the use of nitrogen-fixing plants like peanuts to pull nutrients from the atmosphere and fix them in the ground, naturally restoring the land's fertility. This biochemical rotation is the blueprint for off-world farming. In this diagram, engineered peanut roots convert nitrogen gas into nutrients that spread through the toxic regolith, creating a layer of living earth inside a Martian greenhouse. These macrosystems are the direct results of inventors who focused on protecting and sustaining life on Earth. When the lander finally touches down on Mars, the crew steps out into a world that was once considered impossible to inhabit. Every breath they take through their Morgan-inspired filtration systems and every step they take on Carver-inspired soil is supported by a living archive of genius. This lineage of innovators mapped the stars, tamed the soil and conquered the vacuum, developing these breakthroughs while navigating immense systemic barriers in their own lifetimes. Their work provided the theoretical foundation that modern space agencies now use to execute missions in the deep cosmos. Humanity's arrival on Mars relies on the successful application of these survival strategies, proving that the tools built to overcome obstacles on Earth are the same ones required to navigate the stars.